In this part, we will talk about the second derivative test. In other words, we want to use the second derivative to locate the local maximum and the local minimum. So in the first derivative test, we need the informations of increasing or decreasing, right, to determine where the function has the local maximum, where the function has the local minimum. But in the second derivative test, we don't need that information. We just plug in the derivative, the critical values into the second derivative to determine it is a local maximum and a local minimum, right? We know that the critical point would be the candidate for the local maximum and local minimum. So before we talk about the second derivative test, there is a very important concept which is called concavity. So first we need to determine where the function, we need to determine how the function bend. It will bend up or bend down. Okay, so let's look at some graphs. So this is the function. This is the graphs for certain functions, right? So these three graphs all bends up, right? Bend up. So we give a name which we say these curves are concave up. Okay. So these are the curves that bend down. So we call these curves are concave down. So how the curve is concave up or concave down is called the concavity, right? So now let's look at the test to determine if a curve is concave up or concave down. So now let's look at, we use some mathematical way, right? So this is a concave up curve. And then we look at the tangent line, the slope of the tangent line. The slope of tangent line, that is f prime of x, right? So this is the concave up. We notice that the slope of tangent line is increasing, right? It's from negative 0 to positive, right? From the left to the right. So it's increasing. That the first derivative, the slope is the slope, which is the first derivative is increasing. So if a function is increasing, we know then the derivative of that function, if that function is differentiable, that function would be positive, right? So in other words, it implies that the derivative of this slope, which is the second derivative, right, is positive. So now let's look at this is a concave down curve, and the slope and the tangent line, it's positive, right, to then reduce to 0, then reduce to negative, right? Okay, so we notice that the slope for the concave down curve, the slope, which is f prime of x, is decreasing. So that means the derivative of the slope, which is the second derivative of f, is less than 0. Okay, so these observations gives you the theorem which is called the test for the concavity. This theorem. So we should suppose this function should be the second derivative exists on the interval from a to b. If the second derivative on the whole interval is positive on AB, then this function fx is concave up. In other words, it bends up. If the second derivative is less than 0 on AB, then the function f is concave down. So there is a very important value where the second derivative equals 0, right? So this will give you the next definition, which is called the inflection point. A point C, f of C, is called an inflection point if the concavity changes at x equals c. Okay, for example, let's look at some graphs. So this is the curve bends down, concave down. At a certain point, at this point, it will change the concavity. So this is the concave down. This would be up, right? At this point, it changed the concavity. So this is called the inflection point. Right. The same thing for here. This is up and then down. So at here, this would be the inflection point. It will change the concavity. This is up, this is down. Okay. So how to determine how to find the inflection point? This would be the next theorem. It says if C, f of C, is a point of inflection or inflection point, then either f double prime at C greater than C equals 0, or the second derivative at C does not exist. It's very similar to the critical points, right? But the critical point is for the first derivative. The inflection point is for the second derivative. So now let's look at an example. So this is the function h of x equals 3x to the fifth minus 5x cubed plus 3. So to find the inflection point, we have to look at the first derivative, right? The second derivative. So for the second derivative, we have to compute the first derivative. The first derivative is 15x to the fourth minus 15x squared right? If you factorize it, it would be 15x squared and x minus 1, x plus 1, okay? Then we take the second derivative. We take the derivative for here, not here, okay? Not this one, but this one. It's easier to us. This is what would be 60x cubed minus 30x. So you will have 30x times 2x squared minus 1. Okay, so this one exists everywhere. So we need to find the inflection point. We need to set the second derivative equals 0, right? If you set the second derivative equals, so this would be 30x times 2x squared minus 1 equals 0. So you have x equals 0 or 2x squared minus 1 equals 0. So 2x minus 1 equals 0, so you have x squared equals 1/2. So x equals plus or minus 1 over square root 2, right? Don't forget the plus minus sign. Then you have 3 critical, this inflection point, 0 plus or minus square root 1 over square root 2. So for the inflection point, we're very similar thing. We divide our number line, the domain, into several parts. We locate the inflection, the x coordinate of the inflection point. We locate these numbers. So this would be 0. This is the negative 1 over square root 2. This is the positive 1 over square root 2. So this divide our domain into 4 parts. This is from negative infinity to negative 1 over square root 2. This is from negative 1 over square root 2 to 0, from 0 to 1 over square root 2, and from 1 over square root 2 to positive infinity, right? Like we did before, we should choose a number on each interval, arbitrary number. For example, here we choose negative 1. But instead of plug into the first derivative test, we should plug in to the second derivative test. Second derivative. So h double prime of negative 1. So you do the calculation, right? Plug in negative 1 here. You will see it is positive. So we just care about the positive and negative. So this would be on the whole interval, it's positive. So it's positive. That means from this test, if the second derivative on the interval is positive, so concave up. So concave up, we use this symbol to denote it's concave up. Right. So similarly here, we plug in to the second derivative by negative 1/2, which is on this interval, which will give you also, sorry, I made a mistake. It should be less than 0. Less than, so it's concave down. For this one, plug in negative 1/2 to the second derivative, it would be positive. So h double prime of x should be positive, so it's concave up. And here, h double prime of 1/2, we plug in 1/2, so it's positive, negative, sorry. Then, on this interval, the second derivative is negative, so concave down. On this interval, we plug in positive 1. Okay. It would be positive, so here is the second derivative is positive, so this is positive. So that means this function is concave down concave down on the interval from negative infinity to negative 1 over square root 2 union from 0 to 1 over square root 2. This function is concave up on the interval from negative 1 over square root 2 to 0 union 1 over square root 2 to positive infinity.